Now for space truss we are going to look at a simple problem. It is a problem for oblique 5 in your books by my Page, 9th edition. uh, Now the space truss consists here, as shown here, of a rigid tetrahedron defined by A, B, C and D, anchored by a ball and socket joint connection at A and prevented from any rotation about x, y or z axis by the respective links 1, 2 and 3. The load L is applied at joint E, which is rigidly fixed to the tetrahedron by 3 additional links. Solve for the forces in the members at joint E and indicate the procedure for determination of the forces in the remaining member of the truss. Quite an interesting problem. So how are we going to perceive this problem? First, we need to know that the truss is supported by 6 properly placed constraints, which are the three are at A, that is AX, AY and AZ. And let me show you 3D pointer right here. Y and Z, reaction forces. And then there are links, that is 1, 2 and 3. The load L is applied right here at point E, right? And then we have to find number of value of M. So how many there are M? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So M is equal to 9. Number of joints, we have 1 joint, 2, 3, 4, 5. So we have J is equal to 5. The condition M plus 6 is equal to 3J. So we have 9M, 9 plus M is 15, 3 times 5 is 15. This means it is satisfied. So we have M plus 6 is equal to 3J. Now we have the external reactions at point A, point B and point D can be calculated easily by first step, determine first step, although their values will be determined from the solutions of all the forces of each joint in the section. The first stage is to draw a free body diagram. As we all know, as you can see, we have developed a free body diagram. Now from this free body diagram, we can solve from, as we have seen this free body diagram, we need to first find the projection of EB, FEB, because we know we have the L working and then the component of L is projected on FEB, it is projected on FEC and is projected on FED. So first thing is first, as I've told you, we have to find the R vector from the origin that defines the length EC, like this length, this direction and this direction. These unit directions can be found. Once they have found, then we can find the component of force of L on FEB times the unit vector will give you the direction of force FEB, FEC and FED. So first thing is first, what is the unit vector of if we talk about FEB? So we know this is 3 meters and 3 meters and we are moving from point E to point P, so the component of force acting in this direction should be how much? That is, we know this movement is actually how much? We have negative 3I and negative 3J when it reaches point B, as there is no change in z-axis. So this is how this particular force is moving. And if we take the unit vector, that is minus I minus J. If we take this force and we need to find the value of the component of L on this thing, we know the only projection is how much? 45 degrees. So you take 45 L, FEB is in fact L by under root 2. or FEB is defined as under root 2, half of that is the projection of this particular force. Similarly, we can find the value of FEC, and similarly we can find the value of ED, FED, as you can see it from here. Now, once we have find this value, we are going to say the sum of forces along I, J, K are equal to 0. For that, we have known that L plus FEB plus FEC plus FED should be equal to 0. So we know the L is acting along I-axis. Then we have a projection of FEB under root 2 is simply understood. We know 9 plus 9 under root 2 is going to be under root 2. So we have this unit vector, then we have the unit vector of FEC, and then you have the unit vector and the force or the direction vector in IJK formats. The forces in IJK formats. Once we have these forces in IJK formats, we can reassign the resultant in IJK, and we can say that this whole I is equal to 0 separately, the whole entire J is equal to 0, and entire K equals to 0. And this shows the resolution of forces in their corresponding I, J's, and K's, X, Y's, and Z respectively. From here, we can find the value of L from FEB, FEC, and we solve this equation simultaneously. These three equations, we can find the value of the unknown members, the value of the members in terms of L. Let me repeat it again. We have to find, we were given a simple tetrahedral structure. The only known force was L. We have to find the value of forces acting inside each member, the member which he has asked connected to joint E. The three members that connected to joint E are EC, ED, and EB. So we have to find the forces acting in it. Now the author has pre-assumed the direction of the forces, and he has taken it is moving away from joint A. Once we have found the direction, we also need to find the three-dimensional orientation of these forces, a relative position of these forces, and the best way is to find the direction vector. The direction vector, as we have calculated in our past exercises from chapter 2, chapter 3, and continuing chapter 4, that you can find the first thing is to find the position from origin, that is at A to E, and then A to B, and then you can find the direction vector from E to B. This means you are going to draw a first vector towards AE, and then the second vector towards B from origin. As we know, A is the origin, and then from there you can find the difference, that is EB. Once you find the value of EB, you're going to convert this vector R into a unit vector R. The unit vector R is going to be R, you have calculated, divided by the R magnitude. And you are going to get this value as minus I minus J over under root 2 for FEB. And you multiply it by the magnitude FEB, it will give you the direction in its components I and J. Similarly, you're going to do it for FEC, similarly you're going to do it for FED. Now, the author has done it very simply, but this is how you're going to solve in real time. Once you have solved this thing, you are going to get three equations for the three members right here on top. Now, we are going to write all the forces, that is L plus FEB plus FEC plus FED should be equal to 0. So we have introduced the L as negative because L is directed towards the negative x-axis, and then they have the following components. Now we have three unknowns, FEB, FEC, FED, and we have three equations along x-axis, along y-axis, and along z-axis. So we have three equilibrium equations and three unknowns, and we can solve simultaneously to find the value of FEB, FEC, FED in the terms of L. Now this is a very simple technique, and this is the similar procedures will be adapted for the numericals at the end of the book. Kindly do practice these numericals. It is going to improve your concepts, and you have to apply both method of sections and method of joints simultaneously. Similarly, in this particular example, we have applied both method of sections and method of joints. As you know, the sections involved were FEB, FEC, three sections only, and three sections were actually part of the actual structure. And from these three sections, we solved the joint. So we did not need to go to the moment part. If there were more forces to be unknown and you have limited connectivity of the forces, you can use more equation of moments. But for this particular example, you did not need the equation of moments. I hope you will practice the numericals at the end of the book.